So here we are in lecture 11.4. We're going to look at the next feature addition to our basic maze routing core, and that's multi-layer routing. So you know how to do two-point nets and you know how to do multi-point nets, but you only know how to route things in a single physical material layer. What happens if you actually have multiple layers of wiring material? And the trick is surprisingly simple. You have one layer of the grid for the first layer of the routing material, and you have another layer of the grid parallel, stacked up, lined up for the other layer of the routing material. And just like the expansion process can go out on one layer, it can now go up from the bottom layer to the top, or down from the top layer to the bottom. So as we keep saying, the great thing about the maze routing method is that it's amazingly adaptable. It is amazingly flexible. We can keep adding these cool features. So let's look at how we go from one layer routing to multi-layer routing. So our next application, our next addition of an important feature to the maze routing core is multiple layer routing, multi-layer routing. All chips and all boards have many parallel wiring layers. So chips have 10 plus layers of metal in modern technologies. Boards have 20 plus layers in most advanced technologies. At the level of just this basic expansion process, do we handle multiple wiring layers? And there's a surprisingly simple idea. Parallel grids, vertically stacked, one for each layer. So if you have a metal 1 routing layer and a metal 2 routing layer, you have one grid that's metal 1 and one grid that's metal 2, and they're on top of each other. It's like a 3D array. And you use the vias to access other layers to go from cell XY on one layer to cell XY on the adjacent layer. And there's a new expansion process. So just like we expanded this wavefront out on each layer to the north, south, east, and west neighbors, we're now going to expand to adjacent layers. And I'm going to call this up and down to just keep things simple for the two-layer routing case. You go up to another layer, you go down to another layer using a via. So let's go see how that works. So here's my two-layer example. I've got my little 6x6 grid again, but now I've got a version on the left that says layer 1 and a version on the right that says layer 2. And I've got a source in the upper left corner of layer 1 and a target in the bottom right corner of layer 2. And clearly you cannot route this net unless you can go from one layer to the other, because one of the pins exists on layer 1 and the other pin only exists on layer 2. You're going to have to put a via in here. And there's an obstacle in the middle of layer 1, kind of a vertical obstacle 3 cells high, and there's an obstacle in the top of layer 2, 4 cells wide and 1 cell high, and so there's some places you just can't go on each layer either. So the big idea is that expansion can now go up from layer 1 to layer 2 and down from layer 2 to layer 1. So we're going to do an expansion on this grid to show you how this works, and I'm going to put in a rather artificial constraint. I'm only going to allow vias to be inserted where there's a V in the grid. And so there's sort of a gray box in the grid and a V. And so there's a V sort of in the middle of the grid. It's basically 3 rows from the bottom, 3 columns from the left. And that's in the layer 1 and the layer 2. And then there's another via that's in the rightmost column, 2 rows up from the bottom. This is artificial, but if I don't do this, you won't be able to see anything when I'm doing the expansion because there'll just be too much stuff going on. And this gives a nice, simple example that illustrates all of the right functionality. So the new question is, what happens when you reach a place you can put a via? So let's just sort of start and get to that interesting question. So recall, what's the first thing we do? We find all of the paths that are 1 unit of cells in length from the source, and that is, as always, the source. So we put a 1 on the source. And then we find all the paths that are 2 units in length. And so that's a little diamond of cells, north, south, east, and west of the source. And then we find all the paths that are 3 units in length. And that's another diamond expanding out from the source. And then we find all the paths that are 4 units in length. And that's another diamond expanding out from the source and sort of heading toward the bottom and the right of layer 1. And oh, look, something interesting happened. What happened? I hit a cell that's allowed to have a via. Okay, so what happens next? Well, what happens next is that we're going to continue to expand outward, north, south, east, and west, as appropriate on layer 1. But one of the expansions from the cell with a 4 in it that's gray in layer 1 is going to be up. Up is a neighbor, a cell that's exactly the same location, but in layer 2. So what happens is this. right? We have the same diamond of 1s, 2s, 3s, and 4s in layer 1 on the left, but on the right, the via that's sort of in the middle on the left has a 5 in it, because in layer 1 it cost 4 to get to that cell, and we haven't said that vias cost anything special, so getting to the cell on layer 2 that's in exactly the same XY location just costs 5. It's, as far as we know, it's 1 unit further away. Okay, that's a good model to start with. And so what's going to happen is we are going to continue to do this expansion process, but we're now going to do it on each layer. So now we are expanding on both layers. So what happens? We see all of the 5s on layer 1, which is the diamond of cells 1 unit away from the paths of length 4. And we can see we're sort of heading around the obstacle, and we're heading toward the bottom right corner. There's a single 5 in layer 2, which we're going to use to expand to find the 6s. And so there's a little diamond of cells around the via in layer 2 of cost 6. And there is another layer of cells of cost 6, or path length 6, the cells that are 6 units away from the source in layer 1. And looking on layer 2, another set of cells that are 6 units away. And we can expand the cells in layer 2 to become paths of length 7 that are 7 units away from the source by expanding the 6s north, south, east, and west. And, of course, you don't get to expand the obstacles. And so we go back to layer 1, and we can see the 6s become 7s, and we're pretty close to filling in the whole grid, which isn't going to help because the target's not on layer 1. Right, so we look at layer 2, and the 7s, which are again a nice little diamond around the via, are expanded, and they become 8s, and we get another diamond that's expanding outward from the 7s, paths of length 8 from the source, which are 1 unit away from the paths of length 7. And oh look, something interesting happened. What interesting happened? I hit the target. I hit the target with a path of length 8. Now I do just exactly what you would expect. I do backtrace. I walk the numbers in decreasing order, but now I have to pay attention to the fact that the neighbor with the number 1 unit smaller might not be on this layer. We're just going to see that happen, right? So the thing I'm going to do next is the backtrace. As it says, backtrace through cells and through vias. So we're going to trace backwards 8, 7, 6, horizontally from the right to the left in layer 2 from the target. And then we're going to have to turn. And so we're going to go north to the cell of cost 5. And what you see when you look at that cell of cost 5 is all of its neighbors cost 6. So clearly the backtrace is not going to keep going on this layer. And oh yes, look, this cell with a 5 in it has a via. It must be the case that the 4 that I'm looking for to continue the backtrace is on the other layer. And yes, it is. The 4 that I'm looking for is on the other side. So I'm going to continue the backtrace through the via to layer 1, and I'm going to go from the 4 to the 3 horizontally, and then I'm going to go from the 3 to the 2 to the 1, and as we say, voila, there's the path of 8 units in length that goes through a via that gets around some obstacles and moves from a source cell on layer 1 to a target cell on layer 2. What's next? We take all of the backtraced cells and we mark them as an obstacle, right? And I'm just putting the word via to kind of remind us that not only is there a wire there, but there's a via there, right? So if we have to send some piece of file physically to something for manufacturing information, let's remember that we put a via there, please. And we're ready to go. We can route some more wires with possibly pins across layer 1 and layer 2. Also, all the multi-point net routing stuff will work exactly the same in this environment. So it is a surprisingly simple addition to the core maze routing idea. You just need a 3D grid, and you just need to know that as well as expanding from north, south, east, and west, you also have to expand by looking up to the grid above you and down to the grid below you through whatever your vias technologically allow you to connect to. And otherwise, everything works the same. So just a little quick implementation preview here. We're still sort of talking about feature stuff. Real routers deal with many layers like this. The technology will tell you exactly where the vias can go and to what other layers. And more or less in a modern technology, you can put the vias wherever you want. You can put them on top of each other, so you can have a path that goes from, metal 1 to metal 2 to metal 3 to metal 4 to metal 5 to metal 6 to metal 7. You can put the vias, it's what's called a stack, put a via stack. Um, the maze routing method just works great. Um, I will mention that in real technologies, there are hundreds and hundreds and hundreds of rules about nanometer level effects. Certain places a corner can be, certain places a via on one wire can or cannot be close to a via on the same wire, certain orientations for vias that have asymmetric components. There's lots and lots of complicated stuff. We unfortunately don't have time to deal with it. The way real routers deal with this is they do an abstraction like this grid thing that we're talking about. They embed millions of nets, and then they go in later and they do very fine-grained things on the geometry to sort of fix this stuff. Now, the fact that I just put vias in raises a couple of interesting questions. Are vias expensive? I mean, should I just put them in a zillion places? Um, if I can just route something in a straight line, from a pin on metal 1 to a pin on metal 2, is it a bad idea to, go up to metal 3, route around for a while, come down to metal 2, go up to metal 4, route around a while, come down to metal 1, and then connect? And the answer is yes. Vias are in fact expensive. Should they cost one like other cells? No, absolutely not. It's actually a really bad idea. In real routers, you make vias expensive, so you only use them where they're essential. And that raises a question: what does it mean to make vias expensive? Because so far, the only thing we've seen is every time I use a square on the routing grid, it costs one. And we sort of said that that was like the length. And we even sort of referred to that as the path length, so that when we hit a cell with, say, a 7 or an 8, what that said was that there were 8 cells on the path. That's a great place to start. That's a great place to learn how the core ideas of maze routing work, but it's not the way real maze routers work. We need next a more general notion of the cost of resources in the routing grid. And so let's go do that next.